This last part of this week's lecture is looking at lifting limits for those with low back disability, low back pain. We have that the NIOSH lifting equation assumes that the worker is healthy, the Liberty Mutual tables assume the worker is healthy, and the biomechanical model assumes the worker is healthy. And so how do we evaluate a lifting task if re-injury is likely? A person has a previous back injury. We know that their susceptibility to re-injury is higher. And so how are we looking at improving the task for those that have had back problems in the past? We know that their motion pattern changes. We know that their muscle recruitment changes. Instead of using their back so much, maybe they're using more of their legs, or maybe they have a stiffer back. They often, if they have a back injury, they often gain weight through the years. They might have increased body weight. And through testing, they know that people with low back disability experience higher compressive forces than those without back injury. Chapter 1 presents a method for designing lists for those with low back disability. And so we're referring to Chapter 1, pages 44 through 47. So this particular method, I did want you to be aware of some caveats, some things to watch out for. It was tested on just a limited number of people, 110 people, and only 22 with injury. And so this is really a starter method. They tested at low frequencies, and so a person with a low back disability shouldn't be lifting at any higher frequency or repetition rate. And so it refers to frequencies of less than 1 per minute. Or equal to 1 per minute. The maximum weight that they recommend, given an ideal setup, so close to the body, infrequent, no twisting and so on, must be 25 pounds. And so a person with a low back disability shouldn't be lifting more than 25 pounds. And then still at 25 pounds, there is a medium to high risk of re-injury. Pages 44 to 47 provide you 3 figures that look similar to this, and so I'm just going to step you through how to use these figures for this method. Figure 1.10, and the number is down here, the first figure. This refers to angle of asymmetry of plus or minus 30 degrees, and so no to very little twisting, so twisting the back. Figure 1.1 allows 30 to 60 degrees of twist to either the right or left. And then figure 1.12 allows for 60 to 90 degrees of twist. And so a person with a back injury should not twist more than 90 degrees to their right or left. So it should not twist and lift more than 90 degrees. Okay, so the first step is to pick out how much are they twisting. Very little, moderate, or higher degree of twist. So that's the first factor. Second factor is this horizontal reach distance. This method allows for 2. It allows for within 12 inches. So 12 inches, your arms are basically bent. So they're kept close to the body. If your arms are outreached, 24 inches. So arms stretched out in front. And so you're either 12 or less with your arms bent, or anything beyond 12 will put you into the 24-inch range. Third factor is vertical lift origin above the floor. So vertically, where are you lifting? Is the load near the floor? Is it approximately knee level, waist level, or shoulder level? Okay, so locate one of those. And then once you narrow down those three things, you're going to be looking at the shading. So the shading, wherever those things match, the shading is going to be the degree of risk for low back disability, re-injury. The white areas will be low risk, so low compressive force. The cross-hatched areas, so the crisscrossed areas, are going to be medium risk, so medium risk. And then the grayed out areas you can see listed unacceptable, they're high risk. So high risk. And so going to this example where a person, an employee, is lifting a box off the floor, if he had suffered low back disability, you'd probably be thinking we don't want him lifting that low, but if he were to do this job, if he comes back, returns to this job, the first thing using this method is the angle of asymmetry. You can see he is not twisting his back at all. Okay, so we're at the plus or minus 30 degrees, which is figure 1.10. Second factor is the reach, horizontal reach from the spine. Here you're looking, is it close within 12 inches or is it further than 12 inches? And here his arms, his elbows are not bent, but the load is directly under his shoulders. It's close to his spine, and so I'm going to guesstimate it's within 12 inches. The load is close to him. Third factor, the vertical lift origin above the floor. You can see the box is on the floor, so we're going to start at the floor. And then lastly, your degree of risk and your recommendation. You can see that a close lift that is from the floor at 10 pounds, you have moderate risk. So 10 pounds is equal to your crosshatch area, what is your moderate or medium risk. And so if you're willing to accept medium risk, you can have him lift 10 pounds. Otherwise, anything more, the 15, 20, 25, anything greater than 10 is unacceptable, high risk. What about this figure right here? I don't have a very good photograph, but you can see his back is obviously twisted to the side. You can see his arms are outstretched. They're approximately at an end about right here would be where his hands are, but you can see they're outstretched away from his body. Okay, so in evaluating this, I would say he's twisting probably in the 30 to 90 degrees. So I'd go to the third figure, which is figure 1.12. His arms are stretched out. They're not close to his body. You can see that they're pointing away from him, so I'm going to guesstimate they're 24 inches away. And it looks like his hands would end about right here. If I could see, if I had a better view, that's approximately waist level. And so you can see we cross right here that the low risk, 10 pounds is low risk. Anything above 10 pounds, more than 10 pounds, your 15, 20, 25 is medium risk. And so for this, I would be comfortable with him lifting 10 pounds in this posture, in this photo. Otherwise, anything above would put him at medium or more risk, and I would not want to recommend that. What about lowering the 17-pound tote from the J-hook, the job we looked at earlier? What risk level is it? So which of the figures, is it 0 to 30 degrees of twist, 30 to 60, or 60 to 90? We're looking at the origin. The twist at the origin is equal to 0. So we're back to that first figure, the plus or minus 30 degrees. We can see that his arms are outstretched. And so we're at 24 inches. So arms are outstretched. It was actually 23, but that's above the 12. And then lastly, he's working at shoulder height. So we're right here. We find that no load, so even 10 pounds is unacceptable. So a person with a back injury should not be reaching this far away at this height. That increases the risk of re-injury. Okay, so we have in your textbook, you have those three figures. I just wanted to show you that this is available online through the Ohio Bureau of Workers' Comp. They do have this. If I were to evaluate unstacking a pallet load versus using a scissor lift table, is the scissor lift table good? Does it make the job acceptable? Okay. So again, looking at the worst case where I talked about if you considered all of these sacks, what's the worst case? If the worst case is okay, then it should be okay. Worst case is this lowest sack. Lowest sack will be over in this area versus the using the scissor lift, we can bring it close to his body. We can put it at a good height, so it could be in this area. Okay, but using this website, going to go ahead and go to this website, the Ohio Bureau of Workers' Comp, and it lets you pick healthy versus lower back disorder. So we're considering somebody with a low back disorder. The vertical lift origin, if you're looking at the the sacks on the pallet, we said that the worst case is the floor level. He was reaching not close but far away. And let's assume he's not twisting, and let's assume it's done directly in front of him. We submit that. And the results are that lifting more than 0 pounds is a high risk level. Okay, so lifting at the ground far away is a high risk level. Okay, so that was the original job. If we go back and look at the scissor lift, I'm going to redesign. He still has a low back disorder, same lifter. Now we can raise the scissor lift so that he keeps unloading at waist level. So keep raising it as the sacks go lower. So he lifts at waist level. Now, if it's on a turntable, we can keep the load close to him. So rather than reaching 24 inches away, he can lift only 12 inches away. So we'll assume that. And we'll again assume that he's not twisting. And you're going to find that now we can lift up to 20 pounds with a low risk level. And so 20 pounds with a low risk level as long as we use the scissor lift. And so is it effective design? Here we can lift 20 pounds. Here we can have the person with low back disability lift 0 pounds. And so yes, something like this would be able to keep a person on the job. And then to wrap up this lecture, you've seen this figure evaluated for low back disability. If this person were a healthy lifter, I want you to use the NIOSH lifting equation to evaluate a healthy lifter lifting this box. It weighs 30 pounds. He's lifting it to the third shelf, so right here, 30 pounds to the third shelf once per day, so very low frequency. Assume the fit on the shelf is tight, and so he's got to get it in this little space, which means he needs to use significant control. So use the NIOSH lifting equation to evaluate this task. So you might want to pause it, run your calculations, come back and double check. Okay, so you might pause it. I'm going to go ahead and work through at the origin. My LC is equal to 51 pounds. HM is equal to 10 divided by H is equal to 10 divided by distance between his ankles to his hands is 14 inches at the origin. So he's shown the origin. So 10 divided by 14 is equal to 0.71. VM is equal to 1 minus 0.0075 times the absolute value of V minus 30. In this case, his knuckles are touching the floor. It's 0 inches off the floor, so it's 0 minus 30. Again, that's absolute value, so that'll be 30. So 1 minus 0.075 times 30 is equal to 0.78. My DM is equal to 0.82 plus 18 divided by my D. D runs from 0 inches up to 34 inches. So 0 to 34 is equal to 34 minus 0. And so my DM is 0.87. AM equals 1 minus 0.0032 times 0 degrees is equal to 1. FM equals 1. So you can look up on the table. He's only doing it once per shift, which is very infrequent. And once per day, so a very short duration. And then lastly, my coupling multiplier. This is a box, 90 degree fingers around the edges, and it is a V less than 30, so it's on the floor, V less than 30, and so my CM is equal to 0.95. In this case, calculating my RWL is equal to 51 times 0.71 times 0.78 times 0.87 times 1 times 1 times 0.95 is equal to 23.34 pounds. And then lastly, my lifting index is equal to 30-pound box divided by 23.34 is equal to 1.28. Okay, so that takes care of my origin. Destination, next slide. Destination, when he puts it on the shelf, assuming he is twisting with his feet. So assume twist with feet. He does not twist his back, he twists with his feet. He takes steps to do the twist. In this case, my load constant is equal to 51 pounds still. HM is now equal to, if his ankles are here, is what this is meant to show. His ankles are here, and he is putting it on the shelf. That will be an H of 16 inches. So 10 divided by 16 is equal to 0.62. My VM is 1 minus 0.0075 times, this is 34, V is equal to 34 inches. And so I've got 34 minus 30. That will be equal to 0.97. My DM, I do not have to recalculate that because I'm moving from 0 inches up to 34 inches. It's the same as the origin DM, so exactly the same, so it's 0.87. I do not have to recalculate that, 0.87. AM is equal to 1 minus 0.0032. Again, I said he twists with his feet. He does not twist his back, so he's still at 0 degrees of back twist. So AM is 1. FM, I don't have to look that up again. It's 1. NCM, watch on this one. It's still fair. But now my V is equal to 34, which is greater than 30. So V is equal to 34, greater than 30. That would put my CM at 1.0 because V is greater than 30. Okay, once I have those calculated, I go to the final RWL, the destination is equal to 51 times 0.62 times 0.97 times 0.87 times 1 times 1 times 1 is equal to 26.7 pounds. Lifting index is equal to the actual load weight, the 30-pound box, divided by 26.7 should be equal to 1.12. So lifting index is 1.12. Okay, and again, I had to do the destination here because there was significant control. He did have to reposition, did have to tightly control, did have to precisely control putting the load down at the destination. Final step is I have an RWL of 23.3 at the origin and 26.7 at the destination. I have a lifting index of 1.28 at the origin, 1.12 at the destination. Now I want to do kind of final answer. The final interpretation. RWL origin was 23.3 pounds. Lifting index origin was 1.28. RWL destination equals 26.7 pounds, and the lifting index destination equals 1.12. Okay, so given this, the task LI, you want to use the higher LI as the task LI. Some of the most stressful part. Lifting index is an index of stress, physical stress. So use the higher. So the task lifting index is the higher of the two, is 1.28. This is, according to NIOSH, greater than 1.0. So redesign. And again, I'm using the NIOSH interpretation, not the professional ergonomist recommendation. For your recommended weight limit, you would use the lower. The lower value is 23.3 pounds. And so can you get that paper box from 30 down to 23.3? Can you get the 30-pound box down to 23.3? Maybe if you remove stuff out of it, or if you order from your supplier a less weighted box, you can get it down to 23. Otherwise, if you can't get it down to 23, you would have to control one of the multipliers. We're at the origin, so the origin is where we want to fix. Go back, you're ranking your multipliers, you're looking for what's the smallest multiplier. This would get your 0.71 would get your number 1 priority, 0.78 is number 2, 0.87 is number 3, and 0.95 is number 4. And so starting with your first priority, that's an HM. HM is H at the origin. How do you reduce this? 14 inches. It looks like he's got it pretty close to his body, and so the only thing you might be able to have him step even closer, stagger his feet so that he has one forwards and one backwards. Okay, that would get the load closer to his body. Otherwise, it is pretty close. You might have to go to mechanical assist. Okay, so that takes care of this full and complete notch lifting equation problem. So with that, this homework assignment has you work some notch lifting equation problems. It has you look at some low back disability problems, and then also has you read the extra chapter to look at manual material handling issues.